The sports industry has turned into a testing ground for science fiction. Billions of dollars and millions of tons of steel are now on the line. The modern arena has evolved from a simple entertainment venue into a high-tech bunker. It is a structural machine built strictly to survive extreme physical loads. Global investments in concrete and metal for these mega projects surpass $40 billion annually. The gross domestic product of an entire country like Iceland is only 27. These monumental anomalies dictate city planning. They transform entire economies. But a critical question remains: are these super investments justified when colossal geological risks are at stake? To prevent a massive superstructure from collapsing under its own massive weight, conventional heavy engineering fails. The battle for the survival of the foundation shifts directly to the molecular level. Engineers strip away the heavy metals and isolate the exact chemical formula of the roof. From global budgets, we descend to the micro level. To justify the $2.1 billion investment in Nashville, engineers had to alter the chemical composition of the new stadium roof. A traditional solid canopy demands deep subterranean foundations capable of absorbing massive geological pressures. The design team abandoned heavy industrial bulk for synthetic chemistry. The primary defense mechanism is ethylene tetrafluoroethylene, an anomalous transparent polymer known as ETFE. This extruded plastic redefines structural mass. The ultra-thin membrane weighs exactly 1% of standard architectural glass. One worker easily lifts a section the size of a tennis court, yet the tight molecular bonds deliver extreme physical endurance. The material actively supports 400 times its own weight, pure chemical resistance. The physical environment continuously tests this delicate barrier. Thunderstorms batter the high-altitude canopy. The sharp drumming sound of heavy rainfall on the tightly stretched synthetic film reverberates down through the main steel arches. A single drop of water strikes the curved surface and instantly slides downward, propelled by the self-cleaning molecular friction of the plastic. It funnels directly into the closed circular water management system. Exactly 12,000 square meters of this translucent material form the unbroken upper shield. Sunlight passes freely through the chemical layers, feeding the natural grass field below and eliminating the expensive mechanical complexity of retractable turf trays. Above the turf, the engineering achieves total efficiency. The internal network captures 100% of the falling rain, rerouting the massive water volume into underground tanks for continuous site-wide irrigation and sanitation. Local political disputes over a $100 million public funding grant dissolve instantly against this rigid structural math. The stability of the entire complex depends on an illusion of fragility. A millimeter-thick synthetic film holds back thousands of tons of moving atmospheric water, saving the deep concrete foundation from catastrophic geological overload. If Nashville fought structural weight at the chemical level, Manchester solves the gravity problem with sheer macro force, suspending hundreds of thousands of tons of steel directly in the air. The historic stadium is rapidly shedding its decaying, leaking shell to reclaim absolute global dominance. The new blueprint demands a colossal circular arena for 100,000 spectators. Engineers must execute this mammoth construction inside a hypersaturated urban grid, tightly restricted by complex railway lines. The financial scale of this transformation shatters standard metrics. An initial investment of $2.6 billion triggers a massive macroeconomic shockwave. The mega project generates 92,000 new jobs and injects an unprecedented $9 billion directly into the British gross domestic product. Capital converts into structural power. To support a canopy of this magnitude without a single internal column, architects deploy a mammoth cable suspension network. 3 towering steel masts pierce the skyline. Each spire rises 200 meters above the ground, matching the sheer vertical mass of a 60-story skyscraper. These peaks serve as the primary tensioners. Thick, high-tensile steel cables stretch outward from the top, anchoring deep into the roof frame. Heavy winches engage. The metal groans under extreme mechanical stress. The vast canopy lifts off the concrete structural supports, floating permanently above the grandstands. Brute force, zero visual obstruction. This floating roof hides a highly calculated, darker function. The continuous sweeping geometry turns the entire stadium into a colossal parabolic reflector. Architecture becomes a precise weapon of psychological suppression. The collective roar of 100,000 fans hits the underside of the suspended roof and violently ricochets downward. Mathematical curvature focuses these chaotic sound waves directly onto the center of the pitch. The air visibly vibrates. A suffocating wall of maximum decibel pressure slams into the opposing players, pushing the human eardrum right to the absolute physical threshold of pain. While Manchester defied gravity by suspending thousands of tons of steel high in the air, the next engineering frontier faces a completely different threat from the sky. In Cairo, strict aviation protocols force a massive 50,000-seat arena to literally bury itself underground. The construction site sits directly beneath the active glide path of Sphinx International Airport. Radar sweeps demand absolute clearance. A traditional high-rise stadium would immediately violate civil aviation safety geometry. To secure the $180 million investment, engineers deploy the physics of negative excavation. Heavy machinery carves a colossal void into the solid bedrock, sinking the entire playing field and the primary grandstands well below the zero elevation mark. From an approaching aircraft, the surface looks completely flat. This invisible emptiness from the air perfectly conceals a giant subterranean bunker refrigerator below. A pre-tensioned steel cable net seals the crater, pulling a thin photovoltaic membrane tight across the gap. Digging deep into the crust fundamentally alters the thermodynamics of the venue. The thousands of tons of surrounding soil function as a permanent thermal shield. Instead of fighting the brutal atmospheric heat with mechanical chillers, the architecture utilizes the Earth's natural thermal mass for passive cooling. The deep concrete shell traps the heavier, cooler air inside the pit. The result is a sharp climatic anomaly. At the lowest pitch level, the ambient temperature drops by exactly 10 degrees Celsius. The challenges of solid-state physics in soil give way to computational fluid dynamics in Hangzhou, where the atmosphere itself becomes the main adversary. A single parametric steel louver stands against the storm. This is not merely a decorative facade element, it functions as a precisely calibrated aerodynamic blade. The Hangzhou International Sports Center rises from the saturated swampy banks of the Qiantang River. Building here means erecting a horizontal skyscraper on ground that behaves like a wet sponge. Engineers treat the massive structure like a colossal jigsaw puzzle. Prefabricated steel and concrete components interlock with millimeter precision. Crews assemble a massive arena holding 60,000 seats in just 24 months, a relentless construction pace. But the ultimate threat arrives from the sky. Coastal typhoons regularly strike the province with devastating force. Instead of building a rigid bunker to resist the wind, the architecture slices it. Engineers deploy advanced CFD algorithms. Computational fluid dynamics map every possible storm trajectory before the first steel beam arrives. A digital algorithm calculates the exact attack vector of an incoming typhoon. Then, physics takes control. The deafening roar of the storm slams into the outer shell. The steel lamella physically cuts the high-velocity airflow. Extreme atmospheric pressure shatters against the curved metal geometry. The sheer kinetic energy of the typhoon breaks apart instantly. Outside, chaos reigns. Inside, absolute aerodynamic silence. A gentle, controlled breeze walks through the massive concrete corridors. The entire stadium operates as a gigantic aerodynamic filter. It captures violent wind currents and forces them into a seamless system of natural convective cooling. This structural conversion of destructive weather into passive climate control saves millions of watts in mechanical ventilation, leaving a critical question when nature strikes not with wind but with paralyzing cold. If in China, engineers battle the pressure of typhoons, in Washington, the main load is the heated political climate and national security restrictions. High above the historic stadium grounds, a translucent optical polymer spans the skyline. It forms a massive canopy over a colossal structural frame. The challenge is brutal. How do you grow a living, high-performance grass pitch under a sealed dome without boiling the spectators in an infrared oven? The answer lies in the precise chemical composition of the canopy. Engineers deploy advanced polymer panels designed for selective light filtration. The material acts as an optical bouncer, actively splitting incoming electromagnetic waves. The panels transmit the pure photosynthetic spectrum straight down to the field, feeding the natural turf exactly what it needs to survive. Simultaneously, the chemical structure blocks aggressive infrared radiation. The heat stays outside. This invisible barrier stabilizes the internal climate and strips away the reliance on massive artificial lighting arrays. The system drops total energy consumption by 30%. This thermodynamic precision solves the atmospheric problem, but the urban reality presents a heavier burden. Erecting a megastructure with a budget ranging from $3 to $7 billion, an amount equivalent to the cost of a modern nuclear submarine, requires flawless navigation through a highly restricted national security zone. The project demands an open-concept architectural footprint trapped inside a closed federal fortress. Developers must weave the colossal dome, along with an adjacent district of 6,000 residential units and research hubs, through a dense labyrinth of interlocking federal jurisdictions and relentless legislative blockades. Yet, the engineering ambition pushes far beyond static boundaries. The stadium actively adjusts its own physical shape. Designers integrated a system of variable acoustic geometry directly into the upper architecture. Motorized acoustic panels shift their angles to alter the internal resonance, seamlessly reconfiguring the environment to meet the specific decibel requirements of a professional football game or a collegiate tournament. The massive steel skeleton morphs. The structure tunes its own frequencies, and the deafening roar of the crowd hangs suspended in the air. Hot glycol pulses through a subterranean web of polymer tubes. From the fine-tuning of light and sound in Washington, we move to a brutal fight for survival. In New York, for $1.7 billion, engineers are building not an instrument, but a thermodynamic fortress. $1.7 billion. That is the exact price of survival at minus 20 degrees Celsius. A blinding ice storm slams into a vertical wall of steel and concrete. To block the lethal lake-effect storms, architects stack the stadium stands steeper than any other venue in the league. This geometry creates a physical barricade equivalent to a massive cliff face, violently deflecting the prevailing western winds. Outside, frozen ice tears at the facade. Inside, the strategy shifts to invisible physics. Heating the turbulent air in an open arena is a thermodynamic impossibility. The wind simply erodes the thermal layer. Instead, the stadium attacks the cold with radiation. High-intensity infrared beams drop from the roof grid, falling directly onto the spectators. These invisible waves travel through the freezing air without warming it. The energy converts to pure heat only upon impact with a solid object. The polar wind bites the face at minus 20 degrees, but artificial fire penetrates straight under the skin. Down on the playing surface, the thermal assault continues. Boiling glycol violently circulates under the roots of the turf, maintaining a ground temperature far above the freezing mark. Frozen ice outside, boiling glycol below, invisible heat waves from above. Every layer of this engineering marvel acts as a shield to keep the synthetic fibers elastic and prevent shattered bones upon impact. This mechanical beast is built for extreme endurance. The defensive perimeter must hold its ground in this icy hell for 30 years. But if in Buffalo, engineers aggressively bite into the ground and heat it, in Rome, the earth is touched with the trepidation of a sapper. Beneath the feet lies 1,000 years of history. An electromagnetic wave pulses downward. The ground-penetrating radar, or GPR, scans the subsoil layer by layer. The monitor registers an anomaly. It is not bedrock. It is a 2nd century Roman villa. Hidden cisterns and forgotten masonry walls sleep quietly in the dark. These archaeological ghosts literally paralyze the blueprints. Ancient history dictates the placement of every single 21st century steel pile. Building AS Roma's new megastructure resembles a minefield clearance operation. Engineers cannot simply drive deep concrete pillars into the earth. Instead, they design a distributed support structure. Shallow, low-impact foundations spread the massive weight across a wider footprint, keeping the heavy steel near the surface. The past forces the future to adapt. Every drilling site becomes a carefully negotiated compromise between modern geometry and ancient ruins. Above ground, the structure must handle a completely different extreme force. The new Curva Sud is designed as a single towering grandstand holding 25,000 seats. When those 25,000 fans jump in unison, the rhythmic, earth-shaking impacts generate kinetic energy equivalent to a localized earthquake. Massive seismic shock absorbers and specially tuned steel frameworks swallow this violent vibration. The concrete flexes, the energy dissipates, structural integrity remains absolute. Modern seismic physics secure the skeleton, yet the climate control system triggers a massive chronological shift. Engineers bypass heavy mechanical air conditioning to study the ancient Roman velarium, the giant canvas awning that once cooled the Colosseum. By modeling the aerodynamic principles of the 2nd century, they shaped the new facade of stone and glass to function as a breathing, urban thermal lung. The architecture itself captures, accelerates, and funnels natural wind currents deep into the interior corridors. Ancient mechanics cooling a modern fortress. The digging stops, the past holds the ground. But the constant paralysis of construction due to historical discoveries in Rome pales in comparison to the need to erect megastructures in the chemically toxic environment of old industrial ports. Spain, 1957. Outdated concrete threatens to collapse the ambitions of Europe's greatest club, forcing engineers to take an unprecedented risk for a record capacity of 105,000 people. Reconstructing a giant, crumbling behemoth is structurally more terrifying than building from scratch. The original skeleton is exhausted. A close-up reveals deep fissures and microfractures in the historical pillars. Decades of dynamic stress have brutalized the stone. Now the roar of heavy industrial crushers rips through the stadium. Steel jaws chew through the demolished third tier with a deafening grind and crash. Thick dust fills the air. The sharp crack of snapping rebar echoes across the empty stands. Engineers completely rewrite the material cycle. They pulverize the dead, fractured concrete and fuse it into fresh aggregate for the new foundation trenches. The old shell literally anchors the new empire, but the ultimate engineering paradox hangs above the pitch. The view pulls back to expose a massive steel traction ring. It locks into the largest tensile cable network ever designed for an arena. The scale is staggering. This floating web of interlocking cables supports a load equivalent to several dense city blocks, yet it hovers completely in midair. A traditional solid roof would instantly snap the 1957 pillars under sheer torsional force. To survive, the megastructure must shed weight. Engineers deploy an ultra-lightweight high-tech skin. 30,000 square meters of photovoltaic membrane rapidly unfold across the skeletal network. The material contrast is absolute. Down below sits the brittle, unforgiving physics of aging stone. Up above stretches the relentless elasticity of modern polymers and aerospace-grade steel. The roof does not press down, it pulls outward. The giant cables stretch to the absolute limit, pulling thousands of tons of deadly tension away from the old, fragile columns. If engineers in Barcelona must save a stadium from the crushing weight of 105,000 spectators, the threat in Liverpool attacks from the outside. The aggressive sea salt of the Branley Moor docks devours exposed metal in a matter of months. To build Everton Football Club's new arena on a 19th century maritime footprint, construction crews first had to conquer the water. Heavy dredgers pumped 480,000 cubic meters of sea sand directly into the historic basin. That volume equals the weight of 3 fully loaded supertankers, poured straight into the water to reclaim the land. The brutal visual transformation of the coastline stripped the site of its UNESCO heritage status. But the financial trade-off is massive. The project injects £1,300,000,000 into the local economy. This location demands a chemical war of materials. A standard steel frame standing this close to the Mersey estuary would rot. Total structural failure. The constant barrage of saline moisture triggers rapid, aggressive oxidation. To survive, the stadium operates as a high-tech chemical bastion repelling the ocean. Metallurgists wrap the entire steel superstructure in a specialized, high-density zinc-aluminum alloy. This coating acts as sacrificial armor, permanently neutralizing the microscopic salt crystals carried by the vicious coastal winds. The true sensory weapon of the design lies in the physics of its acoustic breakwater. The sweeping roof canopy mathematically traps the kinetic energy of the crowd. Instead of letting the deafening concentrated roar bleed out across the river, the geometric steel shell forces the shockwave violently downward. It locks the noise inside. The massive single-tier south stand sits just meters from the touchline at the absolute maximum legal incline. Tens of thousands of screaming voices merge into a suffocating wall of sound designed to mentally crush the opposing team. Mathematical models dictate the ultimate endurance of this coastal fortress. The entire anti-corrosive shell is precisely calculated to withstand the relentless ocean oxidation for more than 100 years without a single major structural overhaul. But even this 100-year endurance of the British arena fades before the shadow of a mega project currently breaking the laws of physics on another continent. We are targeting North Africa. Is modern engineering ready for structures that challenge the very concept of human scale? To visualize these impossible proportions, supercomputers process raw blueprints into the exact predictive AI simulations you are watching right now. Tracking this architectural anomaly requires a continuous flow of data. You can monitor the upcoming construction phases by subscribing to our channel and leaving your structural assessment in the comments below. The mathematical models reveal a terrifying reality. European stadium titans will soon look like temporary suburban training grounds. Engineers in Morocco are plotting a facility that completely erases standard dimensions. The foundation grid requires concrete volumes equivalent to 3 heavy hydroelectric dams. This is no longer just a sports arena. It is an artificial tectonic plate, a structural anomaly sprawling across 100 hectares of of desert rock, preparing to drop a continuous aluminum roof weighing 12,000 tons over a concentrated crowd of 115,000 people.